In this video, I want to experimentally demonstrate nodal analysis. To demonstrate nodal analysis, I will use the circuit shown over here. We will first analytically calculate the nodal voltages V1 and V2, and then we will construct this circuit and measure the voltages V1 and V2 and compare them to our analytical values. To calculate the values of V1 and V2, theoretically, we will use nodal analysis, and in nodal analysis, we apply KCL at the two nodes. So let's apply KCL at node 1. KCL at node 1. KCL states that the amount of current that is entering a node should be equal to the amount of current that is leaving the node. I have labeled the directions of current, and at node 1, we can see that the current entering is I1, and the current leaving are I3 and I4. We have previously shown that these currents directions are arbitrary. We can choose any direction we want, and that will not change the result. So the current entering must be equal to the current leaving the node. Therefore, I1 should be equal to I3 plus I4. Now let's write these currents in terms of the node voltages. We see that I1 is flowing through this 1 kilo ohm resistor. On the left side, we have 10 volts, and on the right side, we have V1. Because we have chosen this direction, that the current is flowing towards the right, which means 10 volts must be at a higher voltage, or 10 volts would be a higher voltage than V1. So therefore, I1 can be written as 10 minus V1 divided by 1 kilo. Similarly, I3 is V1 minus 0 divided by 12 kilo, so it's V1 divided by 12. And I4 is V1 minus V2 divided by 1 kilo. Now this is our first equation. We just need to simplify it slightly. And I will multiply by 12 kilo on both sides. That will make it 120 minus 12 V1 equals V1 plus 12 V1 minus 12 V2. Now I have 12 V1 negative, so 13 and 12, so that will give me negative 25 V1, and then positive 12 V2 equals to negative 120, and I can multiply by a minus 1 on both sides, so I will have 25 V1 minus 12 V2 equals to 120. So this would be my first equation. We have discussed nodal analysis in detail in our previous videos, so if you are confused about the directions of the current and the way we have written the currents in terms of the voltages, so please watch our previous video on nodal analysis. Now let's apply KCL to node 2. KCL at node 2. Again, the current entering must be equal to the current leaving. And at node 2, we can see that the current entering is I4 and I2, and the current leaving is I5. So therefore, I2 plus I4 should be equal to I5. Let's check it again. I2 plus I4 should be equal to I5. I2 is, you see, the voltage on the left side of this resistor is 10, and the voltage on the right side is V2. And the current is moving from left to right, which means I have a high voltage on this side and low voltage on this side, and the current is flowing from high to low. And to represent this current in the form of the voltages, I will say that this is 10 volts minus V2 divided by 3.3K. So therefore, I2 is 10 minus V2 divided by 3.3K. I4 is V1 minus V2 divided by 1K. V1 minus V2 divided by 1K. And this should be equal to the amount of current that is leaving the node, which is V2 minus 0 divided by 3.3K. So that is V2 minus 0 divided by 3.3K. To simplify, I will multiply by 3.3K on both sides. So therefore, I will have 10 minus V2 plus 3.3 V1 minus 3.3 V2 equals V2. So we have a single term of V1. So therefore, I have 3.3 V1. So V2 we have negative 5.3 V2 equals to negative 10. This is my second equation. And now I have two equations and two unknowns. I can solve these two equations by substitution, or I can solve it using matrix method. To write these equations in terms of matrices, I will say that the matrix form, we have A times X equal B. In this case, X would be the two voltages, V1 and V2, and A would be the matrix of the coefficients, which are 25, negative 12. So I have 25, negative 12, and then 3.3, negative 5.3. And B is the constants on the right side. So those are 120 and negative 10. With these substitutions in the matrix equation above, we can calculate X. After solving this equation in MATLAB, I get the following values. So V1, the voltage at node 1, is 8.23 volts, and V2 is 7.146. So these are the two voltages at the nodes that we have identified above. Now that we have calculated these voltages theoretically, I want to show experimentally that we will get something very similar if we construct the circuit shown in the figure over here, and we can see that the experimental results will confirm that our theoretical calculations were correct. So I have connected a 10-volt DC supply between the 2 points here, which we can see on the multimeter, which shows 10.14 volts. Now, the theoretical values are shown on the right. At node 1, we should expect about 8.3 volts. So let's measure the voltage at node 1. This terminal is ground for me, and this is node 1. So we can see that at node 1, the multimeter is showing 8.26 volts. Now this is very close to the one that we calculated, however, it is not exactly the same. And the reason for that is that these resistors are not ideal. And each resistor, if it says, for example, 1 kilo ohm, it's not exactly 1 kilo ohm. These resistors have tolerances, and they would be either slightly less than 1 kilo ohm or more, depending on their precision. Now let's measure the voltage at node 2. According to nodal analysis, we should expect 7.146 volts. And let's see what we get experimentally. This is my node 2. And experimentally, I'm getting 7.07, which is approximately 7.1 volt. Our experimental results are very close to the ones that we calculated, and this should improve our confidence in our theoretical understanding of the electric circuits. That's it for today's video. I'll see you guys next time. Bye for now.